Yeah, so welcome back after the holiday, guys. I was thinking, like, yesterday I was solving, I was reading this book for my research and stuff, and I don't know if you can see this book or not. Maybe we'll read it someday. I have heard, I have learned this whole graphical models idea before. So I was thinking, like, how to introduce that to students, and I have seen this independence problem in the entrance examination also. So I was planning to club the thing. And yesterday I wrote a note myself. If you want to see, I will show it to you. Um, for graphical models, and I think I can teach you that. Uh, so writing out notes myself for something. So I will teach you that idea, and I will show it to how you can implement that in normal problems that you know, and how it can help you actually. So let's see. So that was the whole idea of today's I'm like I am me and Sweta has replaced the classes. She will take the class tomorrow. So uh, today I will be doing some revision, and I will start with the graphical problems, and then more revision and problem solving and doubt clearing a bit. It mostly graphical models and doubt clearing. The revision and those things will be if there is time, because I believe that will excite you more. These graphical models than revision, because it's again the same thing. If I start with a simple problem that if I tell you if x and y and IID, okay, or any independent distributions, anything. So x given xy and xyz given xy are independent or not. So that's the question. So if you want to think it logically, I mean using normal ways, you can say that xy is constant, so x is equal to y by c, and xy is constant, so xyz is equal to z. So when x is equal to y by c, like it's almost equivalent to y. So essentially, or you can say x given xy is a function of x and y, where xyz given xy a constant is just a function of z. So therefore, xy, since xy and z are independent, so do you understand? The one idea you can say that x given xy is a function of, let's say x given xy is equal to a certain constant, is a function of x and y. Similarly, but xyz given xy is a constant is nothing but constant times z given xy, which is same distributed xy is equal to c. I'm sorry. Is nothing but constant times xy given xy is equal to c. Now this is same distributed as z, because c is cz, because z is independent of, so it's a function of z, some f dash or f dash of z, or f1 of z. Uh, so therefore, since x, y, z are independent, this is independent of this. Did you get the proof, guys? All of you got the proof? Yeah, simple stuff. No, yes, maybe. What about others? Sure. So, so x given x, y is equal to c is nothing but a function of x and y, okay? The random variables x and y. And xyz given xy is equal to some constant is nothing but, just put xy as a constant, so it's cz given xy is equal to c. Now z is independent of xy, so cz given xy is equal to c is nothing but cz, because z is independent of xy, x and y. This step is because z is independent of x and y, and therefore it's just a function of z, cz. So therefore f of xy and some f1 of z, these are independent, because x and y and so x and y are independent, and z IID are independent. So functions of x and y and function of z some different functions are also independent. That's the result, right? That's the property of independence. So therefore, these two are independent of each other. So that's the basic idea. But there's an interesting thing. We can draw a picture of this conditional stuff. If you remember, I have taught you in conditional probability about the tree diagram. So the whole concept of graphical models, you've already done it. I have taught you in a way, you've already done it. It's based on the fact that probabilities are nothing but you can represent a joint distribution in terms of a graph. In terms of a graph or relationship. For graph, a graph means just like social media network, okay? Some nodes and some connections between them. This is what a graph, nodes and connections. If you ever appeared for Olympiads in in your school days, maybe you have been familiar with this corresponding to combinatoric stuff. So this is the joint distribution, this is graph. Okay, if you have computer science also, you know that what is a graph is, maybe, I don't know. Most probably, yes, I have learned it. So also it encourages which involves, as you know, joint distribution of certain random variables involves relationship between the random variables, right? So as that's the whole point of joint distribution. Okay, it involves a relationship of this random variable. So which involves or picture, it's make a picture of the relationship. So how is the relationship formed? It's very simple. If X influences Y, we write like this. If Y is dependent on X, we write like this. If X is dependent on Y, then we write like this. Like both X and Y are independent, dependent on each other. Okay, we write like this. So in this case, you can write that X XY is dependent on X, and X is also dependent on Y, right? And X and Y has no relationship because they are IID. And then XY also, mm, you know, I mean, XYZ also dependent on XY, and XY is also dependent on Z. So XY is dependent on ZX, but via XY. This is the idea. So XYZ is dependent on X, but via XY. This is very important. Okay. This is very, very important idea. This via stuff. Now let's go back. This is the basic formulation. Now let's go back to the whole theory. The basic theory. And we will not do the mathematical proof of this because it will take time, but I will give you intuitive ideas so that you understand that this is true. So there can be three fundamental structures. Of relationship. So we'll study those three fundamental structures of relationships. So number one is that the dependency can be like this. This is called a chain dependency, sequential dependency. Sequential. Now, I will not take random variables, but I will take real numbers. Okay, I mean real life example. One real life example maybe, let's say clouds. So clouds, if clouds are there, then it influences rain, right? And if rain is there, it influences whether you will be able to play a game or not, whether the game will happen or not. Okay, a game. I mean, game is dependent on clouds, but via rain. Understand this. Okay. Now understand this very basic idea. So we will tell what is independence in this scenario. What do we intuitively mean independence? Independence means that what is independence? That X does not impact Y, right? That is what independence means. Now understand that if let's call this X or A, B, and C. Understand that if you know rain has happened, you know that the rain has happened, you know the rain is falling. Now the question is that will the information that clouds are there in the sky, rain is falling, does the information clouds are there in the sky impact the game? Like impact the game, like in the sense that since rain is falling, you know what is the game, you know, will be. It will be no. So if we know that given the rain is falling, does the information of clouds add any extra information to the game being happening or not? So that's the question. What do you think? You know the rain has fallen. Now will the clouds are there in the sky, adding extra information to the game? Extra information, that is the thing. What do you think? Yeah. There's no right there, you know, I have to say one word. Okay. Okay, so I will do a poll. I will see how many people say no. Yes. So what do you think? Yes or no? If the poll. So the question is that you know the rain is falling, okay? Will the information of clouds, that's the cloud is still there. I mean the rain is falling, the game is always already cancelled. So will is that the clouds is still there, will it affect the game status? That's the question. Will it add any extra information to the game status? This is the question. Okay, I will give you one more minute. The rain is falling, and you already see that there are clouds in the sky. Will it affect the game status or not? Yeah, we'll do 10 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so there are 2 yes and 10 no's. So people who think yes, can you tell me why? I think Anamitra thinks yes. Can you tell me why? Or whoever thinks yes. Anyone, please? Yeah, I mean that's the idea, right? If rain has happened, the game is already being cancelled. Like if the it's like I mean, I'm telling you very definitely, but it's in terms of probability. If the probability of rain is 80%, then the game being cancelled is, let's say, 80%. So now you know the clouds are there. I mean, that does not affect the game status because the game is actually dependent on rain, but not on clouds directly. I mean, the game is dependent on clouds via the rain. See, if you know the rain has happened or rain is highly probable, the existence of clouds does not really matter, right? Because if rain has already happened, you understand, it does not add any extra information. I mean, this is the idea. So, in other words, we say that this channel, I mean, when we know this B, the status of B, this kind of blocks the information pass from A to C. So, given B, information or message, I mean, everything you can say of in probability is in terms of information, cannot pass from A to C. Did you understand the idea? Swati, did you understand? And Anamitra, I don't know, like who said yes. Those who said no, they are right. So we say that this idea is this. So since A cannot impact C, we can say that A given B is independent of C given B, right? So now let's try to understand this model same here. See, in that case, it was X implies XY. Here it was Y. Here it's XYZ. So we know the value of XY. So now it's the same structure. Is independent of. It's beautiful, right? Same structure. So we can mathematically prove it. But I'm just telling you an intuitive way of understanding why it's true and how graphical models can really help. Okay? It's beautiful, yes. So essentially probability is nothing but it's kind of, see, if you understand the difference between probability and mathematics, mathematics says that either this statement is true or this statement is false. But probability says that a statement can be true or false both. Rather, it can take an intermediate value, the chance of being true. So it kind of generalizes the idea. So essentially, probability can impact, it's a different kind of reasoning. Okay, it's a different kind of reasoning than the idea of direct deductive reasoning of mathematics. It's an intermediate reasoning. So that's why you need a new kind of logic, a new kind of calculus for that. And the conditional probability is the basis of that. Conditional probability is the, is the dependence, is the logic. A implies B means B is dependent on A. Understand? If A implies B, then B is dependent on A. So that is the idea. So, I mean, when two statements are not related to each other, one statement does not give any, like, it's a truth value. If you remember the truth value, if you did the Boolean logic in your computer science or something, or in your class 11, that's like a 0 1 value. But in probability, it's taking values from 0 to 1. So that's where the different calculus, different logic is needed. And that's the structure is conditional probability, structure is probability. And this conditional probability helps us to visualize that. Just like the truth table of that, it helps us to visualize this table of this corresponding probability. And it's beautiful. So do you want to do a bit of more about this other two structures, or do you want me to go into the doubt clearing? It's up to you. I have told you the idea, basic idea. Which one do you want? Other two will take another 30 minutes. Which one do you want to do? Okay, what about others? All of you think so? Okay, great. Okay, fine. So I'll also explain two other structures. The, the two other structures are, so one structure is this. First structure, it's called chain, not chain, but series connection. Now, I have not told the beautiful part of it. This is a geometric part of it. I not told the beautiful part of it, how it arises, like why we can write like this. So why we can write this, if x depends on y, then um, I mean we have done this. I will tell that thing at the last. Why we can write like this? If x is y is dependent on x, then why you can write x arrow y? Why you can write like this? I mean the basic idea was what if x influences y, then we can write like this, right? But why? This will answer towards the end. So this first series connection. The next connection is I think one is diverging, one is convergence. So I think this is like this. Yeah. So usually, so the graphical model, this idea was first used in medical science, okay? Because of the flow of symptoms and diseases. So one example can be like this. So here we gave an example of what? Let's see. We took an example of clouds, rain, and game status. Let's take a similar example here. Something implies two different things. So let's say okay, let's take this example. Let's say I have flu. Now flu, or let's say I have COVID. Now COVID can have two different symptoms, right? Or two different outcomes. One is, let's say, dry cough. The other is fever. Or let's say heart attack. Let's say comorbidity. Okay, I think I should take a better example. Just give me a minute. I think there's a better example here. Okay, let's take this one. So now, understand here. So we'll see in terms of information message passing, okay? So if you know that I have COVID, the information that I have COVID does this. So if you know that I have COVID, okay, you know that. So knowing that I have COVID, the information, okay, I think this is a bad example because these are, you can see they're independent, because fever and heart attack may be dependent on each other. So that's the basic idea. So let's say I'm taking a bad example. Let me think of a better example. Uh, okay. Can you think of an example, guys? Of this structure? Okay. So let's take the book example. Gender, height, and hair length. So the corresponding gender, if you know, like you usually the female gender have longer hair length, and statistically it has lesser height. So statistically, probabilistically, yeah, I mean that's a good example. But you can take it together, Vendila. I mean, it's a benign or malignant is the state of a tumor. Okay, so it can be it can be a single variable. You understand? Random variable. Hair length and height are two different random variables. You're understanding? Yeah. So, and since they are not dependent, you don't see any arrow, right? So, but fever can affect um, heart attack, or heart attack can affect fever. Okay, that can happen. I don't know the logic that it does not happen. Okay, so the thing is that you have to also make sure that Y and Z are not connected to each other. You understand? So that's why I could not take that fever and heart attack, because heart attack may imply fever. I don't know. Like it can happen, right? So you have to take the attributes such that they are not related to each other. Hair length and height are not related to each other, right? It's not related, but it's related via a latent variable, the gender variable. So you can find a correlation, but via latent variable. So you can understand that hair length, given the gender and height, does not matter. So, but we'll see that. So if you know the gender, let's understand that. If you know the gender, if you know the gender of a person, let's say me, you know that I'm a male. So does my hair length and my height affect each other? Not really. I mean, they're not even related. Like, given that I'm a male, given that I'm a male, does my hair length, because I can grow my hair, given any height, I can grow my hair as long as I want, right? After 7 days, after 1 year, 2 years, my hair can be this long. Or also I can just make it bald, right now. So the hair length, given the gender I am, why it's called gender? Because why it's related to gender? Because if you see, usually female are shorter and their hair length is more, so they have a negative relation. You can see that. Okay, so therefore the gender is important. You may see a relationship, but the gender is important. And male are longer, taller, but hair length are shorter, so you see a general negative relationship. Do you see the idea? But that's via gender. So once you know the gender, the attributes, I mean information, once you know the gender, the information, and it also goes for the female. Like anyone, any female here can make herself bald or make already have long hair. So anything can happen, right, after some time. So given the gender, it should be given the person, but here we are taking a random variable given a gender. Hair length is independent of height, but if you don't know the gender, they are dependent, because it's open, the gate is open, the information passes. Do you understand? If you don't know the gender, you will see there is a negative correlation, because there'll be two clusters. Okay, there will be two clusters here. If you draw this, if you collect data, you can do this linear project only. I mean, you can do one project of your own. If in the hair length, and you can take height, you will see that hair length is larger, height is smaller. So here is a female cluster and here is a male cluster. Hair length is small, but height is taller. So you will see a negative correlation. This is called Simpson's paradox. Okay, you will see a general correlation, negative correlation. So you will see that, you will think that they're dependent, but they're not dependent, because given the gender, they're independent. Do you see the idea? So similarly, okay, let's make it y. Here also x given y is independent of z given y. Did you understand, guys? All of you? Because it's known here. Information does not pass through this to this. See, the effect of actually this, the knowledge of x can affect y, and knowledge of y can affect z, but here it does not affect y because you already know y. Therefore, x information from x does not pass through z to z via y because you already know y. Do you understand? All of you understood it? Yes or no? Any doubts, guys? Can I move to the next one? No. Okay, so this is the second structure, divergent structure. Now let's go to the final structure, convergence structure. So the convergence structure says that, so let's take an example. Let's take dengue and let's take COVID. This is the flu. Both of them causes flu. Like, it's not flu, I'm so sorry. Fever. And fever causes, let's say, temperature, high temperature. I mean, high temperature is only fever. Okay, so let's say fever causes weakness, and weakness causes fatigue, or something like this. Or let's say this. Just let's take till this point. Now understand this very carefully. What if you know about this point, fever, or this? If you know any one of this, understand this. If you know any one of this, then understand. Then the information, let's call this y, z, x, and x1. So if you know any one of this y, I mean, if you know x or x1, given you know this, the information of y, that you know that fever has already happened or weakness has happened, and weakness happens gives a slight information that fever may have happened. The probability increases. The probability of fever increases. If the probability of fever increases, then probably either dengue or COVID happens. If we know that a dengue might not have happened because it's, or COVID, we know by test that dengue does not have, is probability is very low. So that information gives rise to this effect that maybe it's more high probability COVID because these are the only two possibilities. So the information of dengue given the fever increases or affects the probability of COVID given the fever. Do you understand? So y given fever or weakness is dependent on z given x or x1. So any descendant of x, like these are called descendant of x. Let's call it descendant of x. So y given any x alpha belonging to descendant, I mean this set, either x or x1 or x2 or whatever, because that increases the probability of whatever the descendant happenings, the occurrence of that increases the probability of fever. That descendant is dependent of z given x alpha, where x alpha dependent, where x alpha belongs to the descendant of x. So this is the basic idea. Did you understand, guys? Did you understand? Yeah? Yeah, Swati?
The occurrence of dengue and COVID, I mean, are they happening at the same point, the same
No, no.
instant?
No, they're not. I mean, the probability of them happening at the same time is low. We are assuming zero. We are assuming. You understand? We're assuming it's
So
zero.
how,
But you're right. I'm here.
so how are they dependent? I mean, if a person has dengue,
No,
the
no, no. Given
chances
the
of
fever, the information about dengue So you're right. I mean, if they can dengue or COVID happen together, they can happen together, but the probability is very zero. You understand? That's the idea. I mean, the idea is that dengue and COVID are not dependent on each other. I mean, that's we're assuming. You can take a better example. I mean,
Can you explain once again how are they dependent?
they are not depend. Oh, this one. The idea is that it's given that you know fever has happened. Okay. So since you know fever has happened, then the chance that dengue has not happened increases the probability that the COVID has happened, right? That means, given the fever has happened, if we know the probability of whatever dengue can happen, that influences the COVID. You understand? Because you know the fever has happened, then it must have one of the sources, right?
Yes.
So if you know the dengue does not happen, it means that COVID must have happened.
Oh, so they're disjoint,
I mean,
like
you can think
mutually
in that form.
exhaustive.
And not mutually exhaustive, but you can think that it can come from two different sources. That is the basic idea, yeah. I mean, it can come from two different sources. Do you understand?
Yes, yes, slightly.
Okay, tell me what's causing the problem. You can ask me questions. So essentially, we're assuming that dengue and COVID are the two sources of fever that can happen. Okay, understand this. So if we know that the dengue didn't happen, or probability of dengue happening is very low, that means since the fever has happened, we know that fever has happened. Since fever has happened, and we came to know that dengue, the probability of Y is less. That influences. That means the probability of Z is more. That means Y ka change is influencing Z ka change, given the fever has happened. That's why they're dependent. Do you understand?
Yes, and now I got it. Thank you.
Yeah. What about others? All of you understood? So not only fever, if anything in the chain below happens, I mean weakness or whatever, because that increases the probability of fever. So the theorem is that this is called, you know, this structures of Y and Z pairs. So I had a mistake. Let's call this Y1, Y2. Okay. So these are called D separability. That X and Z are called D separability in these three cases. These are the only three cases. You cannot find any other cases. These are the only three ways it can be D separable. You cannot find any other way. Why? Because X and Y can point into both the other node, can alternate the pointing of the other node, or can into the pointing of other node. So it's three choose one possibility. See, if there is two and there's another node, it can either be like this, or it can be like this, which is same as this, or it can be both of them like this, right? Or both of them like this. So essentially four ways, but this and this are the same. Did you understand? So three possible ways of. Did you understand, guys? Three possible ways. of x of this. So these are called x and y are deseparable. And if deseparable, so we can show that theorem is there. So deseparable if and only if independent. So this is a basic idea. So you can show it's independent and deseparable. Like if you show deseparable, then they're independent. And it has a lot of beautiful applications. So if you can form random stuff, let's say x here. X is dependent upon x and y, let's say x, y. And then this is nothing but x squared y plus e to the power z square a z. And then you can see that these two come together to get x y whole square plus e to the power z square times y square. Okay. And then we can add another w here to get something. So essentially, you can ask whether this is independent of this or not. So let's see the structure. This, 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 this. I'll probably mute this a bit. And then this, and there's another thing coming. Yeah. So it's asking whether this is independent of this given this. Oops. So given this maybe. This is whether it's asking that this is independent of this given this. It's a complicated structure. Is A is independent? It's asking this. Yes or no? Let's check what kind of thing is this. So you can see the structure here. That C is pointing to this, and it's pointing to A, and hence they must be deseparable by the second condition. Divergence form. Hence they must be independent. You see how much beautiful independence is coming up without thinking anything. They can be complicated stuff. You see, they are really complicated stuff. So if you think about this and try to do with all this algebra, it can be really hard. But if you see this structure, the geometry tells the whole structure about information flow. So independence is nothing about information, but information flow. Okay. So this is really beautiful. I find it very, very elegant way of understanding information flow. It's like, I really find it beautiful. Okay, but I will say to you, wow, thank you, SK. I hope everyone likes it. It's because it's not in the syllabus as such, but I hope it encourages you and enhances your knowledge and understanding and perception about probability. Thank you. So Now I will tell you this whole idea of why this. Thank you guys. This, you know, knowledge propagates. So if you have seen, you know the whole idea of multiplicative probability. If you remember that a, if you remember a b c is nothing but probability a given bc times probability of bc, and this can be written as probability of b given c times probability of c. How can I express it? If you see, we are representing this like this. This is c, this is b given c, and this is a given b given c. And the knowledge propagates here to here to here, like this. So you can say the joint distribution is nothing but probability of this times probability of this times probability of this. Or the basic simple example is this: a and then via b given a. If you multiply this, this is nothing but the probability of a given b. So the joint distribution consists of two pairs, a and b given a. It's how it factorizes. Okay. So it's b given a. This is nothing but b given a. So I will tell you in a better way. Wait, I will tell you the explanation. Just give me a minute. There is a bit of an issue because we are seeing A intersection B intersection C. Yeah. So a lot of things out here. This is the basic idea that probability of A intersection B intersection C is nothing but something like this. We ideally should be ideally this. No, we cannot actually write like this because it's not joint distribution. That's the issue. So the addition way. So if you remember that idea of, I mean, the basic idea is this: x and y. Okay. So x times y given x. This is y, but y is dependent on x, so it's y given x. Okay. So x times y given x. I mean, f is nothing but joint distribution. So this y is not but y, but it's y given x, because once you unless you know x, you cannot know y. So it's y given x. So that's the basic idea. I mean, this is essentially what we have done in our, I mean, by this diagram, by this series diagram. If you remember, for addition, we did this divergence kind of stuff. I mean, this three kind of thing comes up. I mean, either x is equal to x or x is equal to b, like that. So similarly here, it's something like that. So, I mean, that's the whole idea I wanted to mention, that if x is dependent on y, then if x influences y, then y given x is not, you know, there's some probability to this, there's some density to this. Hence, this makes sense that x influences y means y given x is a distribution, non-zero distribution. So that's the whole idea. Did you understand, guys, that this is why it makes influence? And this structure makes you find independences. Yep, that's it. Yeah, so that's the kind of graphical model. I hope you enjoyed it, guys. Yeah, Swati?
So I didn't understand the joint distribution well about.
Okay, so the idea is that if x, so we represent it like this because, I mean, if x influences y, we write is as x arrows y, right? Now, how we can make this to form joint distribution? Because joint distribution is f of x comma y. So if this is x implies the density of x, and y is not y, but y is y given x, because y is dependent on x. Okay, so it's f of y given x. It's a distribution. This is nothing but the distribution of f of y given x. Similarly, if you see, so hence when x and y are dependent, it's not one way, but it's usually two ways. It's called undirected graph. So x is dependent on y and y is dependent on x. So in this case, you can write like this, or you can write like this. If you write like this, it will turn out to be f of y and f of y given x. So this is also nothing but joint distribution, right? It's conditional times f of y, sorry, f of x. What I'm doing, it will be f of y given x given y. So product of this gives this. So essentially, this structure also gives rise to joint distribution, where you multiply the corresponding probabilities and go and product all of them to find joint distribution. That's what it's telling. Did you understand? And if it's, did you understand, guys?
Yes, sir.
Yeah. Now, how to find as complex structure probability distributions? There's something called maximal clique. So you find this clique in graph theory, and you find this, and then you find this. You multiply joint distribution of this, this, and this. So that's called the maximal clique method. But that's a different thing so. But the core idea is independence. I hope you understood a bit about this. That was the whole idea. So if you want to read more, you can borrow any book on graphical models. But yeah, you can read it after you get into IIT or ISI, or if you do masters, right? I mean, focus on this is something to and it's after festival, so maybe you're in a good mood. So I shared it with you. Yeah. Any other doubts? Any other questions? Did you like it, guys? Did you enjoy it? Great. Super. Nice. Great. Let's move ahead to doubt discussion now. So I will just close the recording so that I will upload this on YouTube, because other students may find help in it. So I will stop recording and I will upload it again. I will start recording again, okay? So that the class starts for the doubt solving and the problem solving. Thank you, guys.